I'm Malkoski, the team leader for the CU Boulder team for the Department of Energy Geothermal Collegiate competition.
I'm Natalie Alvarado.
I'm Alise Martin.
I'm Alise Gladbach.
And I'm Titus Ellison.
The competition requires that we evaluate a geothermal heat pump at the site of our choosing. Our site is going to be the I Have a Dream Foundation in Boulder, Colorado. We will design for them a ground source heat pump that can eliminate both the heating and the cooling loads of the building, effectively eliminating all natural gas at the site.
The I Have a Dream Foundation of Boulder County is a local nonprofit that supports students from under-resourced communities from first grade all the way through high school. We chose this site because our team values providing opportunities to students from under-resourced communities to ensure they get the same access to STEM education and higher education as everyone else.
A geothermal heat pump operates by combining electrical energy through a compressor with a low temperature heat source to move heat to a high temperature within the building. With this system, we can achieve 4 times greater energy into the building as opposed to the electrical energy required to run the system. This is indicated by a coefficient of performance of 4. We've designed a system like this for our clients at I Have a Dream Foundation to completely offset their carbon emissions and natural gas usage throughout the year. While the system is primarily designed for heating, it also is reversible and serves for cooling in the summer as well at an equal capacity.
For our system design, we used 2 separate coding languages for 2 crucial components. First, we used Ease engineering equation solver to develop the size of the input variable Q low that we need to pull out of the ground. That helped us size this entire system, and then it allowed us to take that input variable Q low and put it into a piping model in MATLAB. This piping model told us how much underground pipe we needed using variables like the grout thermal resistivity and the pipe thermal resistivity and the contact with the fluid and the interior of the pipe. With these 2 variables in place, knowing the depth underground and knowing the size of the total system, we were able to move forward with our engineering design.
So what really sets our team apart is our exploration of design alternatives, our detail in our screening and regulatory considerations, and our collaboration with those in industry and our professors to reality check our design and conceptual models. So our alternatives assessment began with an initial screening process to optimize our design. So first we used our resource assessment to determine the feasibility of drilling depths to reach those useful resources. And so really, in a nutshell, that's considering, are we going to do horizontal or vertical systems? And so a vertical system based on our resource assessment was chosen based on the accessibility of the thermal resources underground and the space limitations at the I Have a Dream Foundation. The next big part of our screening process was our materials, and all of these were based on Colorado's regulatory process, specifically at the state and local level. And so we based these off of economic, environmental, and operational decision making. And so the first major component that we considered was our heat transfer fluid. We ended up selecting food grade propylene glycol at a concentration of 20%. We chose this due to its low environmental impact, its low risk of leakage and corrosion, specifically in relation to HDPE piping, and because it was relatively affordable at lower concentrations. We also used this to work through several combinations of concentrations to maximize our heat transfer and minimize our costs. The next major component that we considered in this screening was the grout. And so this analysis was mostly based on the bond strength to the piping because it was going to contribute to the longevity of our system, the heat transfer, and the thermal conductivities. So we screened through 6 options using our heat transfer model to maximize the thermal resource, and we did this in tandem with our economic analysis. And the main variable here was our borehole length. That served as our primary indicator for our selection, because if you could maximize the heat transfer, you had the opportunity to reduce drilling, which is one of the most expensive aspects of our design. And so with that, our final selection for the grouting materials came to Mix 111. It's a combination of cement sand and bentonite sand, formulated specifically for heat pump applications. It does have a higher cost compared to other materials, but gave us the very large benefit of reducing borehole length and saving us more money as plugged into our models.
We examined 3 different sizes when targeting a geothermal replacement system. The first one, sized at 100%, would be a 15-ton capacity system. The second and third options, sized at 80%, 66% respectively, would lead to a 12 and 10-ton capacity. After thorough NPV analysis, ranging from operating costs, natural gas offset, capital costs, including drilling, grouting, and ductwork, we determined that the full replacement geothermal option is the best overall option.
The I Have a Dream Foundation has a lot of activity in the building, and we want to minimize the amount of time it will take to install the system to avoid disrupting the important work they are doing for their students.
Due to the complexity of the proposed alternative system, feasibility criteria was added to our analysis. The feasibility criteria explains the time it takes to operate, maintain, and fix the alternative systems. We contacted local HVAC companies to see how the alternative systems differ in the operation and maintenance. The 100% geothermal replacement system requires an average of 2 business days to fix, while the hybrid systems are taking longer because they're more complex. Each of the alternative systems don't differ that much in feasibility, but the differences were taken into account into our multi-criteria decision matrix. A curriculum unit was developed as part of the competition. This unit was taught to middle and high school students from the I Have a Dream Foundation. One of our goals is to create an inclusive environment in STEM and engineering, and this curriculum supplement allowed us to work towards this goal.
Lesson 1 introduced the concept of energy and how we use energy, along with providing a preview of renewable energy. During Lesson 2, students learned about geothermal energy and how it is being used as an energy source. We discussed the 3 main types of geothermal energy: direct use in district heating, electricity generation, and heat pump systems, and how each of these systems works. The third lesson went into depth about the 3 types of energy heat transfer: convection, conduction, and radiation. Following this lesson was an activity to demonstrate heat transfer through different soil mixtures. This activity had students learn about data collection by reading and recording data over several time intervals. The 5th lesson brought the I Have a Dream Foundation students to CU Boulder campus for a tour and discussion about the different types of engineering. This was designed to get the students excited about engineering as a possible career path.
And this was our project for the Department of Energy Geothermal competition. Thank you for watching.